morning students. Today we are going to discuss about Schrodinger's wave equation. What we are going at as Schrodinger's wave equation, right? So in the previous class we have discussed about de Broglie's wave equation and Heisenberg uncertainty principle we discussed, right? So there we discussed what de Broglie considered a particle, right, a microscopic particle as a wave, that is as a matter he taken as, and the matter is made up of particles, right? Matter is made up of atoms. In the atoms particles are there, right? So that particles they consider as a wave he considered, who de Broglie, right? In the same way Schrodinger also considered electrons as a waves. Schrodinger also considered electron as a wave, right? So he considered that as a standing wave. How he considered as? He considered as a standing wave, right? How a standing wave will be there? Just we'll see a picture over there. Suppose this is a pathway, there is a pathway, and this is a nucleus, suppose, right? So he considered as, in this way he considered. That means generally what is meant by a wave? A wave means what? What is meant by a wave? Which is having one crust, at least which is having one crust, and one trough should be there, right? Which is having one crust and one trough. If the two things are there, that we calling as a one wave, right? So if any wave is there, one trough will be there, one crust will be there, right? So now here see this, he considered electron as a standing wave, right? Now this is the pathway. This is the pathway. In that pathway, electron is revolving in a particular movement, in a particular way, that is moving. Who is that? Electron, right? Electron is considered as what? A standing wave. Now you see this, suppose here the electron is started its journey from there. Suppose electron is started its journey from here. Now he taken as what? Electron is moving from here to here, right? And then coming to here, right? Now you see this, one trough, one crust, right? One trough here, again one crust. This is one wave. One trough, one crust, another wave. One trough and another crust, another wave, right? Means what? The ending of the final wave, it is the starting point of the first wave, right? So this is the starting point, a trough and crust, again a trough and a crust. The crust of the final wave, that is ending point of the final wave, is the starting point of the first wave. That means here the energy is quantized. Quantized means what? Some amount we are giving, like 1 h mu, 2 h mu, some amount we are giving, right? So that is this mechanical model, this Schrodinger wave equation is like what? In this particular wave, it is having certain energy. How much energy is having? One wavelength, second wavelength, and third wavelength. Three wavelengths are there in this wave. In this, three wavelengths are there. That means you can find the energy of the wave, right? By a formula called E is equal to h mu, we can find the energy of a wavelength, right? So here three waves are there. That means you can find the energy, right? So that is, energy is quantized in the Schrodinger's wave equation. In no other theory energy quantized, but here energy has quantized. That is, here one thing we need to remember, electron he considered as a standing wave. That means this wave will be like this only. Again it will not change, right? So that is a standing wave. That means even the position will change. Now here the trough is there. Now it comes to here. Then it comes to here. That means the position will change, but the number of waves will be same. Then if the orbit size increases, if you draw one more like this, then the number of waves may be increases, right? Then here 3 is there, then there may be 4 or 5 or 6, right? So that is, energy is increasing as the size is increasing and energy also increasing, right? So based on this Schrodinger's wave equation, there is another theory called the Bohr model, right? So based on this model only, Bohr has given one more model of atom, right? So that we will discuss further. Just you remember here what? Schrodinger's wave equation, he considered as a particle, as a standing wave. In the standing wave, the electron is having a wave motion, and in the wave motion, the starting point of the first wave is the ending point of the last wave. That means energy is quantized, we call it as energy is quantized. That means we are saying the particular amount of energy is there. Why? Because particular number of waves are there. If this wave is not connected here, if it is going somewhere else, you cannot find that how many waves are there, right? If it is coming to there only, you can say the starting and ending point of the wave. That by that you can say number of waves are 3, number of waves are 4, you can say it as, right? So by using that you can able to say the energy of the particle, right? So here what I am saying is that energy is in a that particle is moving in a wave motion, right? This wave motion is in a 3-dimensional motion. That wave motion is in a 3-dimensional motion, 3-dimensional motion, right? That means suppose you are taking this as a starting point, origin, then you can consider it as 3 axis, we can take it over there, right? So that is wave is moving vertically, and wave is moving horizontally, and wave is moving along through the z axis. That is x axis it is moving, y axis, and in the z axis also it is moving, right? So that is, just imagine a 3D diagram of a wave. Just suppose any water source is there, suppose any water source is there. In the water source you are creating a disturbance. These all are water. Suppose you are creating a disturbance, then what happens? Waves will be generally developed, right? So waves are generating like this. Now you see that the waves are moving in this way and in this way also, right? And when you see them along through the level of the water, you can find that a level will be there like this, right? That means along through this axis there you find like a structures like this, right? That means what? Horizontally and vertically, and along with that z axis movement also is there, right? So that is we are calling it as 3-dimensional. That is, the wave is moving in a x axis, y axis, and in a z axis also it is moving, right? So based on this axis, based on these aspects, Schrodinger gave one equation that we call as Schrodinger's wave equation. What is that means? See here, dou square psi by dou x square. This we need to call it as dou, right? This is not like 6. Generally we have in math 6, no, that is not like 6. It is opposite to 6. That is we call as what? Dou square psi. That symbol is there, no? This symbol, this we call as psi. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v psi is equals to 0. Right? What are there? Will just I'll tell you. Right. So dou means it is not a mathematical expression. Just it is a quantized value. Right. How it will be means I'll tell you. Right. Here psi is there, no? Psi. Right. So that psi is a wave function. Psi is wave function. Wave function means, so this is a wave we are saying, no? Wave movement is there, no? How the wave is there, where it is started, where it is ended, how much energy it is having, with how much velocity is moving, what energy it is having. These all things we are saying, right? So that all things with togetherly we call it as a wave function. That all the things with togetherly we call it as a wave function. That means instead of saying a wave is starting here, wave is ending here, all these things, we simply say that psi. That means all the things about the wave, it is giving the information by the psi. Right? Now, dou square psi by dou x square in the x-axis, along through the x-axis, how the wave is behaving. That all things given by dou square psi by dou x square, right? And how the wave is behaving in the y-axis, that is given by dou square psi by dou y square. In the z-axis, how it is there, dou square psi by dou z square. And this is the particular constant value. So here 8 pi square into m. M means mass of the particle. Which particle we are taking? The mass of the particle. And h also constant, pi also constant. Planck's constant, this is right. And E means total energy of the system minus V, velocity, into psi is equals to 0. Right? Again, psi means wave function, right? Right. So this is the equation given by Schrodinger, that we call as Schrodinger's wave equation. How it is derived, you leave it. That we will discuss in further classes. or else you don't need of that Schrodinger's wave equation. Just remember, if anyone asks what is Schrodinger equation, you just say this thing, right? And dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equals to 0. That is the equation. Sir, this is very difficult, sir, to be understand and to be remember. Means you can simply say this one in a short form. H cap, this is H cap into psi is equals to E psi. H cap into psi is equals to E psi. That is H cap psi is equals to E psi. Okay. So what is here H means? Here H is what? H cap is what means? Hamilton. That is the name. You don't get confused. That is the name. Hamilton operator. Hamilton operator. Simple. So what is Hamilton operator means? Here you are saying psi, right? For the psi you are multiplying all these things, no, right? We are adding, we are multiplying, we are doing something, all these things, no? Instead of writing all these things, we are writing H, right? Simple, right? So that means H means what? These all things we should do in the place of H. The value what we are getting, that we are taking here as a H. That is H cap psi is equals to E. E means the total energy of the system, and the again psi means wave function. And don't ask me again, here psi is there, here psi is there, in between that is equals to is there. H cap is equals to E, which will be, sir, it should not be equal. This is what we are giving the what we are calculating. This is what we are getting the answer. That is how much energy is there, that we are going to calculate. This is what, how much energy is there, right? That is what Hamilton operator and psi, that H psi is equals to E psi. Simply, children, remember one thing. Schrodinger gave a wave equation. Schrodinger gave a wave equation that depends upon he considered a electron as a standing wave. Standing wave means the wave will be there only, it will not move further. That means the starting and ending position of the ending point of the wave will be similar, right? So by this way you can quantize. Quantize means you can say quantity. Quantize means quantity, number of waves you can say, right? So here we can say the number of waves, right? Here we can say the number of waves. That means energy we are quantizing. We are quantizing the energy, right? So that we can measure the energy of the system. For that measuring, we need to weigh, the electron is where it is moving. The things we need. It is moving in the x-axis, it is moving in the y-axis, it is moving in the z-axis. 3-dimensionally it is moving. So that 3-dimensionally we calculate the energy. That is Schrodinger calculated the energy by using a formula called this one, right? In x-axis how it is behaving, that is dou square psi by dou x square. In y and in z, and the total energy is given. So apart from this, you can remember it easily by H cap psi is equals to E cap. H cap psi is equals to E psi, right? That is what Schrodinger's wave equation. And this thing, this explanation is basic for the further topics like Bohr model and the orbits, all these things based on this Schrodinger's wave equation only. So we consider this Schrodinger wave equation is the basic step towards the explanation of the structure of atom, right? So that is regarding the Schrodinger's wave equation, right?
Hello students, welcome to my channel eScience. Today we are going to discuss about a topic called atomic structure. Atomic structure. Right? So in the atomic structure, again we are going to discuss a topic, electromagnetic radiation. Electromagnetic radiation. In the name itself it is there. Radiation we are calling it as what? Radiation, right? So as generally we know, for other radiations like other energy sources, they need a medium. They need a medium to travel. But here the electromagnetic radiations, they do not require any medium. They can travel in the vacuum also. So such type of radiations, we call them as electromagnetic radiation. What we are calling it as? Electromagnetic radiation. We can define like the radiations which do not require any kind of medium, which can travel in the vacuum also. are called as electromagnetic radiations. Electromagnetic radiations. Right? So let us discuss the properties of the electromagnetic radiations and the characteristics of the electromagnetic radiations. Right? So here we will discuss that how the electromagnetic radiation will be there, means the electromagnetic radiation is travels in a field. There is two types of fields will be there. We are saying what, there is no medium required, we are saying, but there are two fields are there, right? So how the two fields are there we'll discuss here, right? So we'll make it three axes. This is our x-axis and this is our y-axis, and one z-axis will be there like this. Yeah? So three axes are there. As already you know, three axes, that is three dimensions are there. They are like perpendicular to each other, right? Right. Now in these three dimensions, y-axis, right? Y-axis is there, no? So that we calling it as electric field. That I am taking as electric field, right? And y-axis, x-axis I am taking it as magnetic field. I am taking it as magnetic field. What I am taking it as magnetic field, right? So here, if any disturbance created, generally you will take, if any pond is there, any water source is there, if you create any disturbance, if you throw a stone in that, that creates a disturbance which generates waves, yes or no, right? So in the same way, if any electric field, in the electric field, if any disturbance created, that is electric charge creates any disturbance, that we call as vibrations. That is in electric field or in the magnetic field, in both the fields, if suppose any disturbance created in a certain place, that generates a wave, that wave can travel in the two fields. Like I will show you the diagram how it will be. Just try to understand it. So once you see it carefully, see this. So one is on the vertical direction, like vertically how it is going like this, and one direction is horizontal direction, that is for one is to side for my side and for your side. That is, one is vertically it is going and one is horizontally, it is coming my side and is coming to your side also, right? So in these two fields the wave is moving. So the wave generated in a field called electric field and magnetic field. So we named the wave it as electromagnetic wave. That is electromagnetic wave, and the three dimensions are mutually perpendicular to each other. That is perpendicular to each other mutually. Okay, right? And this wave we call as electromagnetic wave, which generates or which moves in the two directions, like electric field and magnetic field. As we know, right hand rule, right? So the see these three fingers are, that is three are perpendicular to each other, right? If you take these three, so one is electric field and another is magnetic field, and one more will be the direction of the wave, right? So see this, the two directions are there, electric field is there and magnetic field is there. The wave is propagating in the two directions, and the one more z-axis is there, no? That we called as direction of the wave. Okay, so that is, we can say it by the right hand rule also. That is, the wave generates in the electric field as well as in the magnetic field. And remember, I said you what, the disturbance creates in a field. If the disturbance created in the magnetic field or the disturbance creates in the electric field, if one is created in one of the fields, the disturbance created, that can disturb the other field also. If the disturbance created in the electric field, that can disturb the magnetic field. If the magnetic field, in the magnetic field the disturbance created, that can disturb the electric field also. Okay? So that is what electromagnetic wave we are saying it as. Electromagnetic wave we are saying it. Then what is mean by a wave? how can you define a wave? What characters are there for the wave, that we need to discuss, right? So that we can say it as wave characters. What I am saying it as wave characters, okay, are characteristics of the wave. So first one in the very important is that wavelength, okay. So wavelength, right? So wavelength, what is mean by wavelength, and how it is denoted means wavelength is denoted by a sign called lambda. A sign lambda. Lambda is the symbol, a notation or a sign for the wavelength, right? How can you define a wavelength, right? So generally wave, what we are saying, wave I am saying, no. So what will be there in the wave? Suppose a wave is there like this. It is a field. In that field, a wave is generated like this. Our wave is propagating like this, right? So see this. These peaks are there, no? The peak points, the top points are there, no? So that we are calling is as crust, and the bottom points are called as trough. That is, any wave is there. In that wave, peak points are called as crust, bottom points are called as trough. Okay. Now how to define the wavelength? The distance between the two continuous crust. The distance between the two continuous crust. You should not say like two crust. We need to say two continuous crust, or two consecutive crust, or two consecutive trough, or two continuous trough. The alternative, that continuous will be there, no? The two continuous crust, the distance between the two continuous crust we call as wavelength, right? So what we are saying, it as distance we are saying. What I am saying, distance we are saying. Distance means what? How to measure the distance in our daily life? Generally we will measure in the meters, centimeters, millimeters, kilometers, right? So same like here, some units are there for the wavelength, right? So we'll write units here. So units of the wavelength, right? So here units of the wavelength are, we can measure in the angstroms. Right? So 1 angstrom is equals to 10 power minus 10 meters. 1 angstrom is equals to 10 power minus 10 meters, and we can measure in the nanometers also, nm. 1 nanometer is equals to 10 power minus 9 meters. Okay? So angstroms, nanometers. So in this, by this we can say what? 1 nanometer is equals to 10 angstroms. 1 nanometer equals to 10 angstroms, right? And 1 in the picometer also we can measure. 1 picometer is equals to 10 power minus 2 meters. So these are the units for the wavelength, lambda. Okay. Right. Then only wavelength is there. No other characters are there. Yes, other characters also are there. That is, one of the character is that frequency. What I am saying it as frequency. Generally we will say no frequency. How can we say the frequency? Suppose a fan is there. Suppose that a fan revolves. How many times it revolves in a second? That is the frequency of the fan. Or suppose a bus is there. The bus comes in a day for 10 times. That means we can say what? 10 is the frequency of the bus in a day. That means in a particular time, how many observations are taken place? That we call as frequency. Same here also. In a particular point, at a particular point, how many waves are passing through the particular point in a second? That we call as frequency. The number of waves, how many number of waves are passing through a point in a second, that we call as frequency, right? So what we are saying, in a second we are saying, no? So the units are what? Second inverse, are the units also, one more unit also is there, that is hertz. Okay, so per seconds, that is second inverse or hertz, right? And that hertz also we can, we can measure like 1 megahertz, that is capital M. 1 megahertz is equals to 10 power 6 hertz, and 1 kilohertz also is there, that is 10 power 3 hertz kilohertz. Okay, so that is what Hz this is. Okay, hertz means Hz. So generally it will come in the hertz only. So hertz means per second. Okay, that is the units of the frequency. Okay? And how this wavelength and frequency are related, just you try to understand here. Here I am taking the two waves. Okay, so one wave contains only one wavelength is there, only one wave is there here, right? And another is there like this. You can see the number of waves, two waves are there, right? You see this. Now the wavelength is more. What is the frequency here? Up to this point, only one wave is there. That is, when the wavelength is more, only one wave is there. Right? Now in the second case, this is the wavelength, right? First wavelength and second wavelength. Wavelength decreased. Number of waves are here 2. Here only one wave is there. That is, wavelength decreased, frequency increased. Number of waves increased. See this. Wavelength increased, number of waves decreased. That is, we can say this like wavelength is inversely proportional to the frequency. Wavelength is inversely proportional to the frequency. So that relation we can take from the wavelength and frequency. Okay. Alright. This is what wavelength and frequency. The next one more also is there. That is wave number. Right? And don't get confused. Number of waves are different. Wave number is different. If anyone asks you how many number of waves means, it is not the wave number. Okay. Wave number is just only the wave number, which is denoted by mu bar. Here frequency denoted by mu. It is mu. It is not like any other mu. Okay. And wave number denoted by mu bar. It is just the inverse of wavelength. Just the inverse of the wavelength. This is what we'll discuss afterwards. Just remember only one thing, that number of waves are different, wave number is different, and don't get confused. Okay, so this where it comes, where we'll use, that we will discuss afterwards. Okay, and next one more is there, speed of light. Or the speed, we can say it as speed. Generally we know what we are saying, the radiation, electromagnetic radiation we are saying, no? So radiation means what? It is an energy source. So when you take the light, speed of light, when you take that, we can represent with the c, and the value we know already, 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second. But here we are taking the particle. So the particle speed we can mention with a v. In the place of c, we can take the v. Right?
Hello students. Today we are going to discuss about quantum numbers. Okay, what are the quantum numbers? What information we can get from the quantum numbers, that we will discuss today. Okay, so before going to the topic, subscribe my channel and press bell icon. So let us discuss what is meant by quantum numbers. Okay, so quantum numbers is a topic. By this we can able to know the position of an electron in an atom. That is, we can able to find the electron, where the electron is there. We can find the electron in an atom. Like suppose we people are there, right? So we are living in a colony, or we are living in a place. How can we say the address? We'll say like first area, we'll say, then we'll say the road number, then we'll say the house number. Yes or no? So like that we are having the address, right? In the same way, electrons are also having some address. Nothing but the quantum numbers are the address of the electrons. Quantum numbers are the addresses of the electrons. How to find the address, that we are able to know this, right? So let us discuss quantum numbers. So there we are having the 4 types of quantum numbers. We are having 4 types of quantum numbers. So in the first one, principal quantum number. Principal quantum number. Okay, it is not principal, it is principal quantum number. Okay, right. So who proposed this? This was proposed by a fellow called Bohr. Bohr has been proposed the theory, quantum number. Bohr proposed this quantum number, right? And it is denoted by a symbol called n. It is denoted by a symbol n. Okay, and the n values are like natural numbers from starts from 1, 2, 3 like that, so on up to n numbers, right? And this principal quantum number, it is giving the information about orbit. It is giving the information about orbit. As we know that what is orbit? So orbit is a particular place or a pathway around the nucleus where the electron revolves. I am telling you again, orbit is a pathway. Orbit is a pathway where the electron is revolving, right? So that is orbit, right? And what information it is giving about the orbit? That is orbit size, orbit energy, and orbit number, okay? So that principal quantum number is giving the information about the orbit size, energy, and number of the orbit. What information it gives, right? So as the number increases, what we said here, numbers are starts from 1, 2, 3, so on, right? So that is, suppose first orbit is there. If you go to second orbit, what happens? Number increases, yes or no? Number increases, automatically energy also increases. So size increases, energy also increases, right? So again size increases, energy also increases. That is, number increases, size increases, so that energy also increases. So that is what principal quantum number, it is giving the information about orbit, right? So let us discuss further. Second one we are having angular momentum quantum number. Angular momentum quantum number. This we can also say it as azimuthal quantum number. Azimuthal quantum number or subsidiary quantum number also we can call it as. Okay, and this angular momentum quantum number, it is proposed by a fellow called Sommerfeld. Sommerfeld has proposed this angular momentum quantum number, right? And it is denoted by a symbol L. It is denoted by a symbol L. And the L values, are n minus 1. That means here n starts from 1 onwards, right? So L value starts from 0, 1, 2, so on up to here n values up to n. So here L values up to n minus 1. Okay, and the angular momentum quantum number, what information it is giving to us? It is giving the information about orbital. Orbital information it gives. So principal quantum number giving the information about orbit. Here it is giving the information about orbitals. Angular momentum quantum number gives the information about orbital. Remember carefully, orbital, right? So here what we are saying here, it is giving the information orbital, no? So how the information will be there means, so we are till now we are having only 0, 1, 2, 3. Till now we are using these orbitals only. Why? Because in the ground state we can fill up to the 3 numbers, right? So that we can represent with a S, P, D, F. That is, the orbitals names we are giving like S, P, D, F. How the orbitals are there, that we will discuss further. Just to remember now, the orbitals, the numbers are start from 0, 1, 2, 3. The values are 0, 1, 2, 3, and the orbitals are what? S, P, D, and F. Okay. Further, if you go to Z, like it is going in like that. Okay. And here, right, principal quantum number giving the information about orbit, angular momentum giving the information about orbital, right? And we need to remember some things like here, how many electrons are there, how many orbitals are there. As already we know, suppose you are already, I told you at starting of the video, in a colony, right? So suppose in a city there are some colonies are there. In the colonies, right? So suppose in a city there are colonies, yes or no? in the colonies, again some small places are there, right? In that, what are there? Road numbers are there. Generally we write address, no? Road numbers. Again in that, house numbers, right? So like in the houses, again there will be 1 BHK, 2 BHK, 3 BHK. That means it is a place for some limited. 1 BHK means only some members will be there. 2 BHK means, that means what? Limited space will be there, no? That can define, no? In the same way, we can also define like atom is there. Atom. Okay. So in the atom, what are there? Orbits are there. Orbits are there. And in the orbits, orbitals are there. Orbitals are there. Again in the orbitals, suborbitals are there. Okay. Again in the suborbitals, electrons will be there. Like in houses, how the people will be there. In the same way, in the suborbitals, electrons will be there. Right? So that is what, how the electrons are there in the atoms, we can say like this simply, right? But we need to give the address by this way. That we will discuss. Okay. So that is angular momentum giving the information about orbital. Okay. Right. So s orbital, p orbital, d orbital and f orbital, that shapes we will discuss. Okay. So let us discuss one more quantum number, that is magnetic quantum number. Magnetic quantum number. Okay. So magnetic quantum number. What do you mean by magnetic quantum number, and how it is giving the information about, right? Right. Magnetic quantum number, it was proposed by a fellow called Lande, right? And it is denoted by a symbol M, right? This magnetic quantum number, it is giving the information about suborbitals. Okay. As principal quantum number giving the information about orbit, angular momentum giving the information about orbital, magnetic giving the about suborbital, right? How the suborbitals are there, we will discuss. How many number of suborbitals are there? Okay, right. And these suborbitals, these values will be like m is equals to 2l plus 1. M is equals to 2l plus 1. Okay. So the values, m values depends on l. Why? Because you need to get the l here. And l values are depends upon the n. So we need to depends upon the principal quantum number. Okay. So that what we saying, magnetic quantum number giving the information about suborbitals. That is, suborbitals are depending upon the orbitals. Orbitals depending upon the orbits. Like, right? Suborbitals depends upon the orbitals. Orbitals depends upon the orbits. Right? So in that way we can say it. And the values are what here? M is equals to 2l plus 1. And the values, the whatever the values after calculating that, we need to write in the form of minus values and 0 and plus values. Minus values, 0 and plus values. Okay. So anything you can take x, like y, any number you can take, but we are writing the numbers over there. Right? So how we will write, we will discuss. Okay. So that is what magnetic quantum number, and we'll count it now. First, how it will be there, we will say it. Right. If suppose we'll take n, l and m values. L values are what? N minus 1. M values are what? 2l plus 1. 2l plus 1, and here suborbital said no, right? Right. If n value is 1, L value becomes n minus 1. N minus 1 means 1 minus 1, it will be 0. 0 means which orbital here? 0 means it is s orbital, right? S orbital. S orbital present in the which orbit? First orbit. So s orbital present in the first orbit. So 1 is I am writing here. Okay. Right. We'll write m values. M values depends upon L. 2l plus 1. L value is what here? 0. That means 2 into 0. 2 into 0 plus 1. 2 into 0. 0. 0 plus 1. 1. We will get 1. Only one value we should write. Remember here, we are writing here 1 means we are writing the one value. One suborbital value we are writing. That means m value. M giving the information about the suborbitals. We are writing one suborbital here. That suborbital I am writing like 0. Remember carefully. We are writing the one quantity we are writing. What we are getting here? Quantity. How many quantities are there? One quantity. What is the quantity? 0. Okay. Right. Let us write again. 2. L value becomes n minus 1. That means 2 minus 1. That means we will get 1. 2 minus 1 means we will get 1. No? This 1 we should write like up to 1. Up to 1. Up to 1 means what? 0, 1 is there, no? That we can write like a, 0 and 1. 1 we should write, up to 1 we should write 0, 1. What is the 0 here? Yes. What is 0? S. Yes. What is 1? P. Right? This S is present in which orbit? Second orbit. So 2S. P present in second orbit. So 2P. Again we will write here M values. For 0 I am writing. For 0 and for 1 I am writing. Okay. 2 into 0 plus 1. We will get 1. Again one value we should write. That is one quantity we should write. I am writing here 0. And 2 into 1 plus 1. Here 1 we got, no? That one we are placing here. We will get 3. Now we should write 3 quantities we should write. We are getting 3 quantities. That means 3 suborbitals are there. In p orbital, 3 suborbitals are there. Remember carefully. In p orbital, 3 suborbitals. In s orbital, 1 suborbital we are getting. In s orbital, 1 suborbital we are getting. Why? Because m values are the suborbital values, right? So here 3 suborbitals. That I am writing like minus 1, 0, plus 1. 3 suborbitals are there. Okay. So I am writing like minus 1, 0, plus 1. As a representative, you know, minus L, 0, plus L, no? So minus 1, 0, plus 1, right? Suppose we will take here n value 3. Here it will be, here what happens here? 3 minus 1, it becomes 2. That means we need to write up to 2. Like 0, 1, 2. So what we will get here? 0 means s orbital. 1 means p. 2 means d. They all are present in the third orbit. So 3s, 3p, 3d. Okay. And y, again we will write here m values. For 0, 3 into 0 plus 1, we will get 1. Again one quantity we should write, only 0. And 3p, 3 into 1 plus 1. 3 is a 3 into 1, 3 plus 1, 4. 1 minute. Sorry, here I am writing 2 only. Okay. We will write here 2 it is. Okay. So 2 into 1 and 2 into 1. Okay. 2 into 1 plus 1. That is 3 we will get. 3 values we should write. Minus 1, 0, plus 1 we should write. Right. And again here 2 into 2 plus 1. We will get 5. That we will write as minus 2, minus 1, 0, plus 1 and plus 2. Okay. See these 5 values we should write. That means in a d orbital, 5 suborbitals are there. In a p orbital, 3 suborbitals are there. In s orbital, 1 suborbital is there. These values 1, 1, 3, again 1, 3, 5 we are getting, no? These are the m. M means what? Suborbitals. The suborbitals are present in the orbitals. See this? First orbital, that is s orbital is there. S orbital, 1 suborbital. Here p, 3 suborbitals. D, 5 suborbitals. Okay. Right. Now we need to remember some things like in each suborbital, there is maximum 2 electrons can be placed. There is maximum 2 electrons can be placed. Like as in a house, suppose in a house, in a one room is there. In that room only 2 members can be sleep. That means there is only chance for 2 members, no? Same way here in suborbitals, in one suborbital there is only chance for 2 electrons. There is only space for the 2 electrons. 1 can exist, 2 can also exist, but 3 cannot be, right? So that is maximum 2 electrons can be placed in a suborbital, right? Right. And next thing we need to remember that number of electrons, right? In a orbit, how many orbitals will be there? Like we discussed here, in the orbitals will be saying will be there. We discussed, no? How many orbitals are there in an orbit? That is n square, and here I am writing it as orbitals in orbit, and next electrons in a orbit, right? So electrons, how many electrons will be there? That is 2n square electrons will be there. Simple thing, remember here, once you see it carefully. Here in first orbit, no? Right. In first orbit, How many orbitals are there? How many orbitals? N square. You make it 1 square. This is 1 square means what? 1. How many are there? Only 1 orbital is there. Second orbit you take. Second orbit. How many orbitals will be there in the second orbit? N square. 2 square means 4. You see this? Here 1 and 3. Right? So 1 and 3. Totally 4. Yes or no? Right. Next third. 3 square. 3 square means 9. You count here. 1 plus 3. 4. 4 plus 5. 9. 9 suborbitals. Right? Now again. First orbital means 1 square. 1 square means only 1 is there. Right? And now that is what orbitals. These are the orbitals. How many number of electrons will be there in each orbit? Means 2n square. In first orbit 2n square. That means 2n square. N square means what? 1. 2 into 1 2. That is in first orbital there can be 2 electrons only can be placed in there. In second orbit 2n square. 2 square 2 into 2 square. That means 8 electrons. See this, totally 4 suborbitals are there. I already told you in each suborbital there is only place for 2 electrons. Totally 4 suborbitals are there. 4 to the 8 electrons. 8 electrons can be placed in that. In third 5 plus 3 8, 8 plus 1 9. 9 suborbitals are there. 9 suborbitals means each suborbital can hold 2 electrons. Totally 9 suborbitals. Right? So 9 to the 18 electrons will be there in that. Right? So that is what principal quantum number, angular momentum quantum number and magnetic quantum number. Right? And one more quantum number also will be there, that I am writing here. Spin quantum number. Spin quantum number. One more is there, that is third one. Fourth one, that is spin quantum number. It is proposed by Uhlenbeck. It is proposed by Uhlenbeck. Proposed by Uhlenbeck and is denoted by S. Yes. Simply what information it is giving? Why? Because already orbits are over, orbitals are over, suborbitals are over, electrons also filled in that. Then what is the use of this spin quantum number? In the name itself there. Spin. Spin means what? Orientation. Spin means orientation. That is how the electron is orienting. As we discussed, right? Electrons are revolving around the nucleus, we discussed, right? So how the electron is revolving? If the electron is revolving in a clockwise direction, if the electron revolving in a clockwise direction, it can represent with a plus half, a symbol like plus half. If the electron is revolving in a anti-clockwise, it can represent with a minus half. Clockwise revolves, that is orientation. If the electron orients in the clockwise direction, plus half. If the electron revolves in anti-clockwise direction, minus half. Simple thing. That is quantum number proposed by Uhlenbeck, and one more fellow also is there, Gaudsmith. So they are proposed the spin quantum number denoted by S. If the electron orients in a clockwise direction, it is represents with the plus half. If the electron orients in an anti-clockwise direction, it will be represents with minus half. Okay? So these are the quantum numbers regarding the how to find the electron and how to mention the address of the electron. Right? Now by using these quantum numbers, we will write the electronic configurations. Right? Remember here we are discussing about orbits, orbitals, suborbitals, electrons, and the electrons how they revolve we discussed. Now we need to write how they can be filled in the orbits, how they can be filled in the orbitals. Right? Directly they are coming to third orbit or directly they are coming to first orbit. How they are coming, whether they are pairing or whether they are singly filling. So that things we need to discuss by following some rules. We need to fill the electronic configurations. Right? So that we will discuss in the next session. Okay children. Hello students. Welcome to my channel eScience. In the last session we have discussed about the quantum numbers, right? So there we discussed what quantum numbers are the address of the electrons we have said, right? Then how to find the electrons and how to write the electronic configurations, how to mention the address of the electron. So that things we are going to discuss now. Okay. So for writing the electronic configurations, we are following a method, that is NLX method. We are following a method NLX method. What we are following? NLX method, right? So once you see that NLX method, NLX, that means N is what here? Principal quantum number. As we know, N is principal quantum number, and that is giving the information about the orbit. They are giving the information about orbit, that is which orbit, in which orbit the electron is there, right? And right, L means what? It is the angular momentum quantum number, right? Angular momentum quantum number, and it is giving the information about orbital, that is the particular electron is present in which orbital, in which orbit, again in which orbital, right? So that is NL. And X is the number of electron, that is in that particular orbital how many electrons are there. As already we know, in the orbital suborbitals are there, in the suborbitals electrons will be there, right? How many electrons are there? 1 is there, 2 is there, 6 is there, 10 is there. So that we will discuss. Okay, so that is we are following a method, NLX method. What we are calling it as NLX method, right? Right. By using this method, in this way only we need to write the electronic configurations by following some rules. What are the rules, right? So first one I am writing here, off-bow principle, off-bow principle. Okay, what is mean by off-bow principle, right? So the lowest energy orbitals, as we know what, in first orbit some electron, for orbital is there, in second orbit also orbitals are there, in third also orbitals are there again. So like that, how many orbitals if you take, so that many number of orbitals will be there, right? So the orbitals, how they are filling, that is from lowest energy orbitals, that is lowest energy orbitals should be filled first, lowest energy orbital should be filled first. Then how to know which is the lowest and which is the highest energy orbital, right? So for that we are having a diagram, right? So that diagram we called as Moiler diagram. What I am saying it is Moiler diagram. Okay, right, I'll draw in a simple way, that is Moiler diagram, right? So I'm drawing here 1s, 2s, 3s, 4s, 5s, 6s, 7s. Again we'll write here 2p, 3p, 4p, 5p, 6p. Again we'll write here 3d, 4d, 5d. Again here write here 4f. Okay, and how to fill that, right? So let us say how to fill that. First orbit is there, no, right? The electron is filling in the first one directly, and the arrow mark is showing the entry of the electron. Arrow mark is showing the entry of the electron, right? Again the electron will go into the 2s. Electron will go to the 2s. Again you don't write like it is coming to back side, you write from top only, right? Then again 2p to 3s, then 3p to 4s, then again like this. Okay, it will be like this. Now we need to write the energy series of these orbitals. This diagram we call as Moiler diagram. Now I will write the energy series for this. All right, energy series, see it carefully children. First electron enters into 1s, no, it is 1s, right? Lower energy, no, so 1s. The next electron enters into 2s, the next electron enters into 2p, don't say it as 3s, go to top again, 2p, next coming to 3s, again go to here 3p, next coming to 4s. So with I'm not having enough space, so I'm writing here 4s, the next 3d, the next 4p, 5s, so on like this. So it is filling like this. So in this way, that is the arrangement of the orbitals, that is the arrangement from lower energy to higher energy. The orbitals are arranged like this. In this manner only we need to fill the orbitals, in that manner only we need to fill the orbitals, right? So first 1s should be filled, then 2s, then 2p, 3s, 3p, 4s, 3d. Then you will get doubt here. Here writing, what we are writing here, 4s we are writing, and here 3d we are writing, no? That is 4s means 4 is there, 3s means 3s is there, that is 3 is smaller than the 4, no? Then why we are writing the 4s? means here one rule is there, that rule we are writing like n plus L rule. What we are saying it as n plus L rule, right? According to the n plus L rule, if you are taking the 4s and 3d, if you are taking the 4s and 3d, here write n and L values, n and L values will write here. In 4s, what is the n value according to NLX method? NLX method, right? NL 4s, that is n is the 4, L is the S means what? In the azimuthal quantum number we discussed, no? 0, 1, 2, 3, S, P, D, F we discussed, no? Right? So that is L value will be 0. So it will be 4 only. When we take in the n plus L, it will be 4. Now coming to 3D, n value will be 3, L value will be 2. Then it will be 5. Who is bigger than, who is higher here? So obviously 3D is the higher. So 4s is filling first. Right? So that is, we are filling the electrons as per Bohr principle. That is, Bohr principle means what? Lower energy orbitals are filling first, then it is going to higher energy orbitals. Okay, that is a one rule. In this one rule you need to write, so two cases, you need to learn the two cases, like Moiler diagram you need to learn, and you need to learn the n plus L rule also. Okay? And then next one I am writing here, Hund's rule. I am writing here Hund's rule. We can call it as Hund's rule also, right? So what is meant by Hund's rule? Means in a s orbital, how many suborbitals are there? Only one suborbital, right? In p orbitals, 3 suborbitals are there. In d, 5 suborbitals are there, right? So if the p is having the suborbitals that we wrote like what? -1, 0, +1 we wrote in the magnetic quantum number, or that you can mention like px, py and pz also you can mention like, right? So these orbitals are having the same energy. These orbitals are having the same energy, that we can call it as degenerate orbitals. Degenerate orbital, that means orbitals which are having the same energy, which belongs to same orbitals, are called as degenerate orbitals, right? Coming to the Hund's rule, the degenerate orbitals should be filled first with 1 electron each. The degenerate orbitals should be filled first with 1 electron each, then the pairing should be starts. Pairing should be starts after degenerate orbitals are filled with each 1 electron. Okay, so that is Hund's rule. Hund's rule. So how that is we will discuss here, right? Suppose we'll take carbon. We'll take carbon. We'll take. So carbon number is what? 6. Carbon number is 6. So we can write the configuration as per Bohr principle, right? And we know what? In each suborbital there is only 2 electrons will be there. So according to that, s orbital can hold 2 electrons. S orbital can hold 2 electrons. P can hold 6 electrons. D can hold 10 electrons, and F 14 electrons they can hold. Yes or no? Right. So here we are writing the carbon configuration, that is 1s2, 2s2, 2p2, 1s2, 2s2, 2p2. Okay, right. So see this, we can mention like this. In s orbital 2 electrons are there, only one suborbital is there, 2 electrons. Again in 2s, s orbital 1 suborbital is there, 2 electrons. Again in 2p, 3 suborbitals are there, no? In the 3 suborbitals, these 2 electrons should be given to degenerate orbitals. It should not be filled like this. They should not be filled like this. Okay, so we need to write like this. Okay, that is, the pairing should start after filling the degenerate orbital. That means if suppose nitrogen you take, 1 electron comes to here. If suppose oxygen you will take, 1 electron comes to here, next electron comes to the pairing. But we need to do what? First we need to fill the degenerate orbitals with 1 electron each, then only pairing should be starts. Okay, so that is Hund's rule. Right? And next one, Paulie's exclusion rule. Paulie's exclusion rule. What is mean by Paulie's exclusion rule? Right? So let us say no 2 electrons, no two electrons of same atom, no two electrons of same atom having the 4 quantum numbers same, that is, if you take any atom, any one atom, if you taking, in that one atom no two electrons are having the same 4 quantum numbers. That means in an atom all the electrons are having the different quantum numbers. That means at least one quantum number should be different. Suppose we will take a example, helium we will take. Suppose, as we know, helium configuration 1s2, two electrons are there, right? So the two electrons will be, one is in a clockwise, one is in anti-clockwise direction, right? Now let us write here, two electrons are there, no? In 1s2 two electrons are there, right? That is 1s, one electron is there, 1s, two electron is there. If you write the all the quantum numbers for these two electrons, right? N, L, M and S. Okay, here also N, L, M and S we will write for that. Okay, right. How it will be now? According to NLX method, here 1s1 is there, N value is what? 1, S value is what? S means 0. If L value is 0, M value will be 1. That we can also mention with a 0. Why? Because we need to write one quantity, 0. S means what? Spin. First electron is in a clockwise direction. If you showing the upward arrow mark, that is clockwise direction, and that is plus half. Okay, coming to second electron, ns2, sorry, 1s2 is there, n means 1, again here 0, M value also 0, S value, second electron is the second electron, anti-clockwise means minus half, right? So these are the rules we need to follow while writing the electronic configurations. You see this here, in this, two electrons are there in the helium, two electrons are there in the helium. Quantum numbers are, 3 of the quantum numbers are similar, but the 4th quantum number is different. That is, no two electrons of the same atom is having the 4 quantum numbers same. That means 4 cannot be same, 3 can be same, but 1 is different, no? So that is the thing, Paulie's exclusion principle or Paulie's exclusion rule, right? So these are the rules we should follow while writing the electronic configurations. Okay, so that is Bohr principle. That is, what is my Bohr principle? Lowest energy orbital should be filled first, right? And in that we are writing the Moiler diagram and n plus L rule. And next Hund's rule. Hund's rule means what? The degenerate orbitals should be filled first with 1 electron each, then the pairing should be start. Then Paulie's exclusion rule is what? No two electrons of the same atom having the 4 quantum numbers same. That is Paulie's exclusion rule, right? So by using these rules and in the method of NLX method, we are writing the electronic configurations of the electrons. Okay, right.